This is the geometric series. It's the sum of a to the k for all values of k from 0 to infinity. And its value is well defined as long as the absolute value of a is less than 1. But there's actually a slightly different series that emerged in a homework problem I did a while back. It's the sum of k times a to the k from k equals 0 to infinity. And of course you can just look up this value, but I found it very interesting to derive it from the geometric series, and it's actually not too hard. So what we do is we take this equation and we just differentiate by a. Now, since differentiation is a linear operator and this is just a sum of individual terms, we can just differentiate each term individually. It's actually a little more subtle here because we have an infinite sum, and for infinite sums there are some corner cases where this is not possible. But for the case here it works out. So we have k times a to the k minus 1, and we also differentiate the right side, of course, which is 1 over 1 minus a squared, and then two minus signs that cancel each other. Notice that the left sum starts at 0, but it has a k, so the first term is 0 anyway. So what I'll do is I'll replace that 0 with a 1, and I haven't committed any mistakes. Now I want to write the sum again, but this time start at k equals 0. And I will replace k by k plus 1. So it doesn't matter if I start at 1 and write k, or start at 0 and write k plus 1. But it allows me to write the exponent as k, since k minus 1 plus 1 is just k. And the right side didn't change, of course. But the left hand side now has a very interesting form. So we have the sum that we're actually interested in, that is sum of k equals 0 to infinity of k a to the k, and then we have just another geometric series, just 1 times a to the k, and this value is well known. And this allows us to compute the value of the series that we're actually interested in. So if we just bring that 1 over 1 minus a to the other side, we get k equals 0 to infinity of k a to the k equals a over 1 minus a squared. And that's the value of this series.